Hello everyone, my name is Jason Gregerson. In this video, we're going to create a key for the first practice exam for exam 1. So we'll start off with question number 1. It says state the values if they exist given the following matrices. And part A says find the dimensions of C. Well, we would say C is a m by n matrix, where m is the number of rows, so that's 1, 2, 3 rows, and n is the number of columns, 1, 2. So it looks like C is a 3 by 2 matrix. Next we'll go on to B. B says find the A23 element of the matrix A. So we go to the second row, third column, right there. So A23 should be 0. So once again, those are marking the row and then the column of the position. So C says go to the B12, so that's first row, second column. So that would be my value for B12. D says go to the C23, so that's second row, third column. So that one looks like it does not apply because there is no 2, 3 position of the matrix C. Then we have the sum of two matrices. To add those matrices, we are just going to add them component-wise. So these are both 3 by 3, so we can do this addition. And we'll just add these two components. 1 plus 0 is 1. Then 0 plus 1 is also 1. 1 plus 0 is also 1. And we'll just keep doing that to get the next row of 0, 3, 1, and 0, negative 1, 2. Now we go to A plus C. We're trying to add this matrix to this matrix. And I could certainly add these components, and I could add these components, but I wouldn't know what to do with this last component. So I can't do this addition. This one also does not apply. In this case, we have to recall that to add two matrices, they have to be the same dimension. Now we'll go to problem 2. Problem 2 says, given these augmented matrices, so I know these matrices are augmented matrices, the coefficient matrix in the right-hand side vector, I need to label them as REF or RREF. So the first thing I'm going to do is mark the pivot positions. In the A, I have these 3 pivot positions. Now I notice that they're not all 1, and there aren't 0 entries above those pivot positions, so it can't be an RREF form. The question is it REF? And I have these as my pivot positions, and I have zeros below them, so it looks like it is in REF form. Now the next example, I have my pivot positions right here. I have zeros below them, I have zeros above them. This one looks like it's an RREF. I see those pivot positions are all 1 as well. Question 3 says for each of the row-reduced augmented matrices below, first circle the pivot positions and then state which of the following best describes a solution set. Is it a single point, a line in R3, a plane in R3, or no solution? So the nice thing about this problem is that these are all already RREF, or almost RREF matrices. So for instance, this first one, I see my 3 pivot positions of my augmented matrix. In this case, because I have a pivot position for each row, I can see that if I wanted to write out the solutions, it would be exactly x1 equals 2, x2 equals 4, and x3 equals 2. And so these values are fixed. This is just one point in 3 space. Now, instead of calling them x1, x2, x3, I could think of them as x, y, z in the 3-dimensional coordinate system. And the only values for x, y, and z, or x1, x2, x3 in this case, are 2, 4, and 2. Just that point. So this would be a point in R3. Now we look at the next one. If I think about what the solution would be, I can identify my pivot positions, and it looks like I have one free variable. So I have a column that doesn't have a pivot position, so this would mark my free variable. Now I also have a row of all zeros, and that's okay because that means there is not a pivot position in that right-hand column. So I know there are solutions, and there's one free variable, and because there's only one free variable, I can already say that this is going to be a line in R3. Now if I wasn't sure about that, I could always try to generate the solution. My first equation would be x1 plus x3 equals 0. The next one would be x2 equals 2. And I could write that in parametric vector form to be x equals, well, x1 is equal to a negative x3 if I solve that first equation for x1. x2 is just equal to 2, and x3 is just free. And so once again, if I write this in parametric vector form, it would be 0, 2, 0 plus x3 times negative 1, 0, 1. And so if I think about plotting this, I am taking the sum of two vectors, this vector and any multiple of this vector. Well, if I just plot 0, 2, 0, and I call this x1, x2, and the x3 directions, for instance, that would be 0 in the x1 direction, 2 in the x2 direction, and 0 in the x3 direction. So I'm just talking about this vector right here. And if I add, for instance, 0 of this vector, I would get this point. But if I add 1 of this vector, this goes from this point, and I travel negative 1 in the x direction and 1 in the z direction up here. So if I took this vector plus 1 of this vector, I would get this point. If I took this vector plus 2 of this vector, I would be up here. 3 of the vector, I'd be up here. Negative 1 of the vector, I'd be here. And so I can see that if I change that multiple, I can generate different points on this line. So that's another way that we can see that this is a line in R3. And maybe yet a third way we can see it's a line in R3 is that our solution will have one free variable. So we're looking for a linear function with one independent variable in R3, and that would be a line. Now for C, we can look at our pivot position here, and it looks like we have two free variables, so we might be tempted to say that our solution should look like a plane, because a linear function of two independent variables would be a plane in R3. However, that last row tells us that we have, if we write out that equation, it'd be 0x1 plus 0x2 plus 0x3 equals 1. And there are no values of x1, x2, and x3 that satisfy that equation. So in this case, there are no solutions. Another way to think about that is we have a pivot position in that far right column of an augmented matrix, and that tells us there should be no solution. Now question number 4. Determine whether or not the following sets of vectors are linearly independent or linearly dependent. And then we want to justify our answers. And it's not just the decision, it's the justification that's just as important. So in the first case, I see right away that I have two vectors. Anytime I have two vectors and I'm trying to determine independence or dependence, I just have to see if they're multiples of each other. So in this case, I say that 8 times 1/2 brings me to 4. So I have that factor of a half. And if these two things are dependent, they must all be factors of 1/2. 2 times 1/2 brings me to 1, and 1 times 1/2 brings me to 1/2. So these ones are linearly dependent. Because if I call this one V1 and this one V2, or 1/2 of V1 is equal to V2. So they're just multiples of each other. Now we go on to the next one. The next one I have three two-dimensional vectors, three vectors in R2. And so right away I know that these ones must be linearly dependent. And why does that make sense? Well, any three vectors in R2 must be linearly dependent. We have too many vectors given their dimension. And one way you can think about this is for a set of vectors to be linearly independent. One way I can test for that is by throwing them all into a giant matrix. I just create a matrix of these things, and I could row reduce it. And I would look at the pivot positions. And the columns with pivot positions identify linearly independent vectors. But in this case, if I look at this 2 by 3 matrix, I can only possibly have two pivot positions. So there can't possibly be a pivot position for every column. And so I'm bound to have one column with no pivot position, meaning that vector is just a multiple of the other vectors. Now we look at part C. Part C has four-dimensional vectors. So I can't talk about the number of rows and columns of this matrix helping me make this decision. And so I might potentially have to write this into a giant matrix and do the row reduction to see if I have a pivot position for every column. But luckily I don't. Right away I can identify that I will not have a pivot position in this column. Another way to think about this is the zero vector is an element of this set. And any set of vectors that contains a zero vector is automatically linearly dependent. So once again, here I'm using my three shortcut techniques for determining whether a set of vectors is linearly independent or dependent. The more general process would be to throw them all into a matrix and do the full row reduction. And then if I have a pivot position in every column, those vectors must be linearly independent. Question number 5 says label the following statements as true or false. So we're going to go through each one of these questions and talk about why they're true or false. The first one says the augmented matrix. Here I'm have two columns of some matrix A and then a vector B. It says this augmented matrix has solutions if and only if B is in the span of A1 and A2. So what does it mean for B to be in the span of A2? It means there's some linear combination of those two columns that equal B. That's the definition of being in the span of these two vectors. But that's just a vector equation. That's a vector equation, which is similar to the matrix equation, AX equals B. And to solve that matrix equation, we would look at the augmented matrix and row-reduced final solution. So if this thing has a solution, then this statement is true, and B is in the span of A1 or 2. So this one is true. Next one says the vectors 2, 1, and 4, 2 are linearly independent. So once again, if I have just two vectors, all I'm checking to see is that they're multiples of each other. Here I can see that if I take 2, 1 and I multiply it by 2, I get the vector 4, 2. So they are multiples of each other, which means this is not linearly independent, but rather it's linearly dependent. Part C says the set of all linear combinations of a set of vectors is called the span of the set. And this is really just the definition of the span of a set of vectors. The span is the set of all linear combinations. So this is true. D says given an M by N matrix A, if M is less than N, then A must have linearly dependent columns. So I think the best way to approach this problem is to draw a picture. So I'm going to try to draw a matrix, an M by N matrix where M is less than N. So I might have 2 columns, for instance, and 3. So I might have 2 rows, for instance, and 3 columns. This would be a 2 by 3 matrix, so M would be less than N. And now it's saying that A must have linearly dependent columns. Well, one way we can tell whether columns are independent or dependent is to look at their pivot positions. This matrix that I've drawn, where M is less than N, can only possibly have M pivot positions. It can only have leading entries to rows for each row. That would be the most. And so because I have 3 columns, there can't possibly be 3 pivot positions. So this is exactly true. That one of those columns must be a multiple of the other columns. Therefore, the set of columns must be linearly dependent. The next one says that given an M by N matrix A, if M is greater than N, then A must have linearly independent columns. So once again, let's draw a picture of this. We have more rows than columns. And this is saying that if this is the case, that the columns must be linearly independent. Well, they certainly could be linearly independent because I could have a pivot position in each one of these columns, for instance. But do they have to be linearly independent? The answer is no. I certainly could have 2 columns that are just multiples of each other. In this case, I have a matrix, M by N, where M is greater than N, but those columns are not independent. So this statement is false. F, I'm given a matrix. It says the matrix is in row echelon form. So I'm going to circle those pivot positions, and I have zeros below them, and everything else looks good. So I should be true. This one is in row echelon form. Now the next one says the matrix is in reduced row echelon form. So this is REF. So once again, I would circle those pivot positions, check to make sure all those values are 1, and also check to make sure that I have zeros below and above each of those pivot positions. In this case, I don't. So this one would be false. H says elementary row operations on an augmented matrix can change the solution set of the associated linear system. And this is a very important one. This one is definitely false. And it's because of this being false, they do not change the solution set, is the reason we can use row reduction to find solutions. So if we start with some augmented matrix, 1, 2, 3, 4, 1, 2, for instance, that represents a system. And when we do row operations, we're going to transform this into some other system. And the assumption here that this theorem is going to give us is that in that process of row reducing, in that process of doing elementary row operations, we are not changing the solution set. So we're simply transforming this to an easier system to see the solutions, but the solutions are the same. So this is an important one that is false. The columns of A are linearly independent if there is a pivot position for every row. So once again, it's best to draw a picture of a matrix and kind of put this to the test. So here I'm saying that there's a pivot position for every row. So what if I make a matrix that looks like this? There is a pivot position for every row, but are these columns linearly independent? They are not, because one of those columns is the zero vector. And any set of vectors that contains a zero vector is a linearly dependent set of vectors. So this one would be false. J says that the columns of an m by n matrix A span Rm, then the equation Ax equals b is consistent, or has solutions, for each b in Rm. So first of all, what does it mean for the columns of this matrix to span Rm? So I have an m by n matrix, so I have m rows and n columns. So the size of each of these columns is m. Now if I take a span of the columns, that's like taking a linear combination of each one of these columns. And they're saying if the columns span Rm. So that means I can find this linear combination for every b in Rm. So no matter what b we're talking about in Rm, I can always write it as a linear combination of these columns. That's what it means for these columns to span Rm. But once again, this linear combination of these columns is just a vector equation, which is the same thing as this matrix equation. So saying that that vector equation can always be solved, there's always linear combination for any b in Rm, just means that that matrix equation can also be solved for any b in Rm, which is the second piece. So this one is true. K says that a system with free variables is consistent and has multiple solutions. Now it's very tempting to say this one's true because we know that free variables are associated with systems that have infinitely many solutions. However, that's only if they're consistent. This says a system with free variables is consistent, which isn't always true. So for example, I could write this system and it would be 1, 0, 0, 0, and 0, 1, 0, 0, and 0, 0, 0, 1. So if I look at this augmented matrix, I can see that there is a free variable, x3 would be a free variable, but that last equation would tell me that 0 equals 1, which is not true. So this is a system that has free variables, but is not consistent. So this one would be false. And the last one says a homogeneous equation is always consistent. Well, the homogeneous equation is Ax equals the 0 vector. To be consistent, we have to have a solution for this system. Well, if I look at the trivial solution, x equals 0, this is always a solution. If I plug in x equals 0, I get a times 0, which is always equal to 0. So this is always a solution to the homogeneous equation, which means that homogeneous equation is always consistent. So this one is true. In question 6, we're given a linear system of linear equations. Part A says write out the augmented matrix for this system. So to write out the augmented matrix, we simply take the coefficients from each of these variables. So I have 3, 3, 3, and I'm going to augment it with the values on the right-hand side. So that'd be my first row. My second row would be 1, 3, 1, and then 9. 1, 3, 1, 9. And the last one would be 1, 2, 1, 7. So this would be my augmented matrix. Part B says find the reduced row echelon form of the augmented matrix by hand, showing all key steps. So I'm going to start with my augmented matrix. I'm going to start doing row operations. My first row operation is to take 1/3 of row 1. That will give me a first row of 1, 1, 1, and 5. My next row operation will be to take R2, the second row, and subtract row 1. So I'm going to use this pivot position, which I've created here, to eliminate this value, to put a 0 there and put a 0 there. So this operation, I'm going to leave row 1 the same. R2 minus row 1 will give me a 0. I'll get 3 minus 1, which is 2. 1 minus 1, which is 0. 9 minus 5, which is 4. I'm going to do another row operation. I'm going to take R3 minus R1. If I do that, I will get 1 minus 1 is 0. 2 minus 1 is 1. 1 minus 1 is 0. And 7 minus 5 is 2. So now I have this one. Now my next step is to take 1/2 of row 2. So I can put a pivot position of 1 there. Another option would be to switch row 2 and row 3. That also would have been a good option. My first row in either case is going to stay the same. My second row, when I divide it by 2, or multiply by 1/2, I'll get 0, 1, 0, 2. And I have 0, 1, 0, 2 in the bottom row as well. Now, my next step is going to be to take R3 minus R2. So I've created a pivot position here, and I'm going to use that to put zeros below it. My first row stays the same. My second row stays the same. And when I take R3 minus R2, I get 0, 0, 0, 0. So now I've done the forward process. I've established all the pivot positions that I can. Now I have to go the backwards route. Now I have to take my pivot positions and make sure there are zeros above them. So my next step is to take R1 minus R2. Row 3 will stay the same. Row 2 will stay the same. And now R1 minus R2 is 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 0 is 1, and 5 minus 2 is 3. And so this would be the row-reduced echelon form of my matrix. Part C has me use that row-reduced form to write out the solution of the system in parametric vector form. So I'll start by rewriting this as a system. My first row of my reduced row echelon form matrix is x1 plus x3 equals 3. The next equation says x2 equals 2. The last equation is a bunch of zeros, which tells me that x3 is a free variable. Now I can solve those for those leading terms. So I get x1 equals 3 minus x3, x2 equals 2, and x3 equals my free variable x3. I'll write this in parametric vector form, so I'm writing that my solution has a vector x. This vector has components x1, x2, x3. So to get an expression for each of those, I've already solved for them, so I have those expressions right here. So it'll be 3 minus x3, 2, and x3. Now I want to write this as some number times a vector plus some number times a vector. That's my parametric vector form. So to do that, I'm going to first write all the constant values, 3, 2, and 0, plus x3 times all those coefficients, negative 1, 0, and 1. Now, while that might be a little tricky to see, it might help to go backwards. Once you've seen the solution, go ahead and do that multiplication, taking this vector times x3, and then do the vector addition, and you'll see that you get back to this position as well. So this is my solution in parametric vector form. All right, problem 7 says solve the following matrix equation. So I'm given this matrix equation and I want to solve it. Now, one of the best ways to solve it is to do exactly what we did in problem number 6, is to write out that augmented matrix and go through the row reduction. So that's what I'm going to do. I have 1, 0, 2, augmented with this right-hand side of 1, 0, negative 2, 4, 0, 0, 1, negative 2, 1. I'm going to do the row reduction. My first step is to take a negative 1/2 of R2. My first row will stay the same. I will get 0, 1, negative 2, and 0. And my third row is 0, 1, negative 2, and 1. Now I'm going to take R3 minus R2. First row will stay the same. Second row will stay the same. My third row, when I subtract these two, will be 0, 0, 0, 1. Now at this point, I am in row echelon form. And once I get to that form, I should take a look at my augmented system here, because at row echelon form, I can determine if there are solutions, and if so, how many solutions there are. In this case, I can see by this last row, there is a pivot position in the far right column of my augmented matrix, which tells me there are no solutions. Another way to think about that is if I look at that equation that's represented by this last row, it would once again be 0x1 plus 0x2 plus 0x3 equals 1, and there are no values of x1, x2, and x3 that can make that true. In this case, there are no solutions. Question 8 says, let T be the transformation that takes x1 and x2 and maps it to the following, to x1 plus 4x2, comma 0, comma x1 minus 3x2, comma x1. So a first step is to find the matrix A that implements this mapping, that does this transformation. Well, this matrix that we need is just going to be the transformation, be a matrix whose columns are the transformations of these special vectors, the transformations of the columns of the identity matrix. Now, one question is, what identity matrix? Well, T is taking in vectors that are two-dimensional, vectors that have x1 and x2 components. So it's taking in vectors from R2. And it's mapping those vectors to four-dimensional components. So I have components where these commas are. So here's one component, two components, three components, four components. So it's taking vectors that live in R2 and mapping them to vectors that live in R4. So I'm taking inputs for R2. So I'm going to look at the two columns of the 2 by 2 identity matrix, which look like this. That's what my E1 and E2 are going to be. And so if I look at the transformation of these two columns, that should give me this matrix that I want. Well, if I look at the transformation of E1, if I plug in x1 equals 1 and x2 equals 0, what will I get for an output? Well, if x1 is 1, I will get 1 plus 4 times 0, which should be 1. And then I'll get 0 my second piece, and then I'll get this for my third piece. If x1 is 1 and x2 is 0, this should give me a value of 1. And the last component is just x1, which should give me a value of 1. So that is T of 1, 0. Now in a T of 0, 1. So now x1 is 0 and x2 is 1. So in this case, I would get 0 plus 4 times 1, which would be 4. 0 in the second position. 0 minus 3 times 1. And I would get 0 in this last position. So this is the matrix that represents that transformation. Part B says is the transformation one-to-one onto both or neither. And one way I can determine that is to row reduce this matrix A. So if I take A and I row reduce it, 0, 0, 1, negative 3, 1, 0, the first operation is going to be R3 minus row 1. So row 1 stays the same, row 2 stays the same, then I get 1 minus 1 is 0, and negative 3 minus 4 is negative 7. And then I'm also going to take R4 minus R1, in which case I will get 1 minus 1 is 0, and 0 minus 4 is negative 4. Now I'm going to do two operations at once. I'm going to take row 3 and move it into the second position. I'm going to swap row, or I'm going to move this one up. I'm going to move this row of zeros all the way to the bottom. Put that one at the bottom. But not only am I going to move R3 to R2, I'm also going to divide it by a negative 7. That will give me this value. And then lastly, I'm going to take R3 plus 4 times R2. And when I do that, I will get a 1 here and zeros here. Now I'm in REF, and I can identify the pivot positions, pivot position here and pivot position here. So it looks like I have a pivot position for every column. This tells me that the columns are linearly independent, and if they're linearly independent, any solutions I find would have to be unique. I wouldn't be able to have multiple solutions. I wouldn't have any free variables. So in this case, that means the transformation is one-to-one. However, there is not a pivot position for every row. That tells me that this transformation is not onto. And that makes sense with my original matrix as well. If we think of the different values in R4, if I thought about this matrix or this vector 0, 1, 0, 0, there is no linear combination of the columns in A that could get me a 1 in that second position. So that would be one vector in R4 that we would not be able to be mapped to from some x in R2. Number 9 says, describe the effects of the multiplication of the matrix A, and then is this transformation one-to-one onto both or neither? Justify your answer. So what is this matrix doing? Well, let's just take this matrix and multiply it by some value x1 and x2. If I do that multiplication, I will get the vector x1 and negative x2. So all I'm doing here, when I put in points, if I put in the point 1, 2, for instance, it would map to the point 1, negative 2. If I kind of do a little plot of that in R2, if I took the point 1, 2, it would map to 1, negative 2 down here. If I looked at the point 1, 1, it would map to 1, negative 1. So it looks like all this is a reflection about the x-axis. Now, is that transformation one-to-one onto both or neither? Well, we could talk about those in terms of the transformation, that we should be able to map every point to some other point, and also that mapping would be a unique mapping. Or we can also think about the matrix itself. This looks like it has a pivot position for every row and column, so this would be both. This transformation is both one-to-one and onto. Question 10 says complete the following properties involving these matrices. So we have some matrix properties. These are going to be stated in the class, so we can justify them in a more formal proof. Right now we're just going to go through and state these. So if I had the transpose of the sum of two matrices, I get the sum of the transposes. If I take the transpose of a transpose, I'm just back to the matrix I started with. If I take the transpose of a product, I have the product of the transforms, but in reverse order. So I can switch the order there. B, if this matrix is invertible, then the inverse of the inverse is just the matrix A. And then if I take the inverse of a product, it's similar to the transpose property, where I take the product of the inverses, but once again in reverse order. And the last one, I have the distributive property. But I have to be careful with my distributive property and make sure that if I am multiplying on the right-hand side by this matrix, that inside after I distribute it, I'm still multiplying on the right-hand side. So I have to be a little bit careful with that one. All right, and the last page of the practice exam has me perform some operations given some matrices. So I have an A, I have a B, I need to perform the following operations. So one, A plus B. Well, right away, I can see that I can't take that addition of two matrices because they're not the same dimension. So this is NA, I cannot do that operation. B says find the transpose of B. So to do the transpose, I take the first column of B and make it the first row of B transpose. And the second column of B and make it the second column of B transpose. So that should be B transpose. I'm going to go to C, which is the product of the two matrices. So I have the matrices, I'll copy them down here. 1, 0, 2, negative 2, and B was 1, 0, 2, 2, and 0, negative 1. And so A is a 2 by 2, and B is a 3 by 2. So because these inside values don't match, I can't do that multiplication. So this is also not applicable. Now what about the product B times A? Well, this one I should be able to do. So I have 1, 0, 2, 2, 0, negative 1 times 1, 0, 2, negative 2. And so if I take this column times that row for my first component here, I have 1 plus 0. I'm going to keep going down to the next row. Here I'll have 1 plus 4. And then the last one should be 0 minus 2. I do that same operation here for this next column. I will get 0 plus 0, then 0 minus 4, and lastly 0 plus 2. And this should simplify to 1, 0, 5, negative 4, negative 2, and 2. And the last one is the inverse of A. Now I could write this a bigger matrix with A on the left and augmented with I on the right, and go through the row reduction to find the inverse matrix. But because it's a 2 by 2, I have a formula for this. It should be 1 over this product, which is negative 2, minus this product, which is 0. And then times a matrix that looks like A, but where the values on my main diagonal are switched, and the values on my off diagonal, I have a sign change. So that's my formula for the inverse of a 2 by 2. I'll simplify this up a little bit. It looks like this is negative 1/2, and if I multiply my matrix by negative 1/2, I get a 1, 0, 1, and negative 1/2. Now on the exam, of course, I would want to check this by taking that matrix times A, and hopefully I should get to identity. And that's the last problem for this practice exam, and it concludes this video. Thank you.